Hello? How are you?
I'm doing fine. How are you guys doing?
Good, good.
Cool. Yeah. Good morning.
Good morning. Hello, Adama?
Hi.
Hi.
How are you?
All right. So, did someone want to start us off with an update?
I can start if you want.
Okay.
I don't have a lot of things to say. I'm keep going on working on Unity because last week I was working on Blender, and now I'm making the whole thing on Unity and setting up the VR environment. And for now, I can move hand. I put the spaceship, and I'm working on the interaction.
Yeah, that's great. So thank you for the update, and it sounds like you're coming along. And Hussain, how are you?
Yeah, fine, thanks. Okay, so as I mentioned, I'm not doing GSoC.
Yeah.
GSoC I'm not a GSoC participant. I'm not happy to update, but I'm happy to update you guys on what I've been up to and what I've been doing. So and just dipping my hands into whatever I can get my hands on, but so been working on the breast cancer computer tomography with the breast cancer computer tomography approach using the Janospheres by taking advantage of X-ray steerability capacities. That's under Mission Gordon. Things are coming along quite nicely, and we're doing a lot of writing on the book chapters and getting some figures together to get the papers published. So, excuse me. So always busy with a lot of stuff. Always busy with a lot of stuff, and getting ready to most likely move out to California pretty soon to start working for the company I've been devoting a lot of time and energy and resources to.
Mm-hmm.
And ideally, I'd be working part time, or in my spare time on the project under Dick Gordon and myself. So we'll see where things go with it. So yeah, I think so the company's based in Davis, so I'm most likely going to be living in Sacramento, NorCal. Yep. Yeah. I think it's probably more affordable than the Bay Area. Probably more affordable.
Yeah.
And compared to like LA, I don't think Sacramento is actually too difficult to live in. I don't think so.
That's nice.
So the by the way, hey Adama, which engines are you using? You said Unity, the Blender, right? Just wanted to ask.
Yes.
Yeah. Yes. Okay. Have you thought about using Unreal?
Actually, I wanted to use Unreal for the beginning, but I'm working on another project in virtual reality with two mates in my school, and they wanted to use Unity, so I decided to use Unity as well.
I mean, they're both good. They're both good in their own ways. I think Unreal is just a lot better for physics in general. So for physics-based simulation. So I've been using it, but I'm also trying to take advantage of some other ones I've been talking about with Bradley. So basically, to perform the simulations from X-ray steering approaches, Bradley put me in touch with some other engines to use. Like there was Console, but I don't have a student license, so I'd have to pay $3,000. I'm like, no, thank you. I'm sure not being able to use Console isn't that big of a deal. So there were a few others, and it looked like Moose, OpenFoam, and Elmer were some ideal ones to use. So I'm looking for ones. Okay, excuse me. I want to ask you guys if you know of any sort of physics simulation engines that might be really good for simulating X-rays, how they can be steered, approached, and beamed between different objects and surfaces. Unity, Unreal, and Blender are all right, but those things are primarily based for like animation for games and stuff. When there are some other engines that are more specifically for scientific research, so if anyone has any suggestions, I'd be open to hearing that. So,
have you seen what Slicer 3D is using in terms of its dependencies?
3D Slicer.
forget if it's 3D slicer. Yeah, but it's built on BTK, ITK. It's out of Brigham and Women's. And it's very much a radiology framework. So like they would have a lot to that community would have a lot to say about this kind of.
Yeah, I think you mentioned it. I think you might have mentioned that. Okay, so.
Yeah, I'll go over that paper I sent you in a little bit, but yeah, I think
they have a very regular developers meeting too. So you can get a lot of good support, or like a lot of good feedback on a regular basis from that community.
Yeah. Yeah, a lot of tools are specialized for certain things, and sometimes you can adapt them. It just really depends on how open they are, like how much you can manipulate the code or how easy it is to program things in that environment. So, oh, that's good. Oh, do you have anything else?
Yeah. So yeah, on there's a lot of stuff I can share as well too, but on a more like so we're trying to be very, very thorough with getting the details and stuff together. Like, say for example, so like the tumors that we might need to detect, they have a very spherical nature. So we'd have to, for example, engage in template mashing for a different approach. Like tumors maybe like from 1 millimeter to 4 millimeters in diameter. We'd have to have different templates in size. We could look at the techniques like adaptive histogram equalization to improve the visibility of the tumors against different backgrounds. And then, see how in best ways we can accommodate for slight variations in tumor sizes to make sure like our approach is robust across different imaging scales. So all of these all put together, it's ultimately the tool and the software you use. It's like for me, whatever I can just get the best approach with, whatever I can collect the most information with, and do the most simulations with too. So mostly been using Python, MATLAB, Octave sort of things for like basic maths and physics simulations. But and this is it's good to have this discussion because obviously they all have different purposes. Like Blender is really good, and Blender you can do simulations with. You can, but Blender is not really meant for that from a scientific research point of view. It's meant for art, for animation, for design. But I will say though, Blender can have some very specific details that some other software, like even Unreal, you can't quite get to, and I think that's really, really, really cool about Blender, in some ways. And I guess I also wanted to ask, this is why I want to post this to Orel too. For you guys, as scientists, as researchers, if you had some simulation or tool or software that you could use, say, for simulating like reinforcement learning agents and seeing how they interact with one another, what would you want from that? Because I want to ask too, because I want to think for myself in my future in terms of like, if I were to design my own software or my own engine or something moving forward for scientists and researchers, what would be the best things that people might be looking for? So it's always things to keep in mind.
Any answers to that? Any preferences?
Sorry, do you mind saying that again?
Basically, if you were using some 3D tool, 3D simulation software, some program, some engine, whether it's like making a video game, like making Super Mario Bros. In 3D, or if it's for something more scientific, like you need to simulate how agents perform and how they move and interact and adapt to different environments. What would you want from the engine? What would you be looking for? Okay, in terms of like maybe. If I were to ask you, what would be your biggest priority as a user? I'm gonna ask you that. How's that? So, yeah.
But again, like, what am I trying to do from that? Because like this sounds kind of like the discussion we had about 3D engines, and like how Blender is different than Mujoko, and versus Godot or something like that. And so it's like if you're making movies, or if your focus is on geometrical interactions, like with Majoko, like each one has kind of its strength, even though to some degree they're all similar. You know what I mean?
Yeah. Of course.
So just in this scenario, what's my goal for the framework? Like, is it scientific simulations?
Okay. Like, let's say the scientific simulations, right? What would be your priority about what you as a scientist with your PhD trying to do your project?
Yeah.
Or I guess if you don't have a PhD, if you're doing your project, what would be your biggest priority that you would want or what you would need so you can use it as effectively as possible? Would you say, interactability, ease of access? Is it like the ability to yeah.
Sure. Yeah, so then it might be it might be something like like I don't want to say ease of coding as much as like interpretability. So like Phoenix, right, spelled with FE, like has just a real focus on making the simulations, the math, as kind of as simple as possible in terms of turning that into complex simulations, right?
Yeah.
So you can think of it as kind of like ease of coding, but you can also think of it as like just being able making your code readable and interpretable.
Okay. Yeah. Like if the answer is like ease of coding, then obviously because it is what it is, and like I mean, maybe not obviously, but like ease of coding, then make it like Python based, right? Like, easily, or
right.
maybe MATLAB based. MATLAB is MATLAB. Excuse me.
Yeah.
I
mean, check out Phoenix. Phoenix is a great tool.
Yeah. I mean, ultimately, like from the perspective of academics and scientists and researchers, one thing I've always come to understand is like being able for them to translate their knowledge to something that they can use and work with for experimentation and research purposes, right? So that's essentially so you got your background in like you have a background in physics, right? Pretty damn well Maxwell's equations. How can I easily be able to study that and research that in a scientific simulated setting, just right in the computer in front of me, So ultimately, being able to just write and type the equations on my keyboard and see and perform the experiments right there, that's easily one of the best things and the easiest things to do. And yeah. I mean, and also, just on a more like general audience perspective, right? Like people talk about like what's appealing to you about a software versus on another software. You guys remember how like in Microsoft Word, Bill Gates made the like Clippy?
Yeah.
And it's like, oh, I see you're writing a letter, like dear so and so, can I help you out with that? Here's some tips. And I'm like, I always wanted to make an engine that would have its own little animal or a creature or some person is gonna. I think someone joked about making Blendy for Blender, and it'd be like the Blender logo with like eyes on it, and it'd be like, oh, cool, you're trying to perform a simulation using geometry nodes. I can give you some keyboard shortcuts and it's cool stuff like that. That's because it's funny because that's what I would like look for. Because I'm not even trying to just be like overly because that stuff's important too. So, anyways, that's just what I wanted to pose to people.
Yeah. So I guess I have two things I'd mention. The first is sort of expressibility, and that's a term that they use often. It's a newer term that means what can it model, what can it represent. And so it's easy to say kind of build a platform specialized for a certain type of representation. So if you model things in springs, that's easy to program maybe, but it doesn't model every instance of what you want to do. The same thing with like in NetLogo, you have that problem too, where you have your agents and you can't necessarily model the agents. You can't model them as too complex of an individual agent. You have to kind of limit what you can use as in a representation. So if I wanted
Yep.
to say use simple rules, I'd be in business. If I wanted to use like a neural network, I wouldn't necessarily be in business. And then that's one thing I would look for is a build that for sort of flexibility, but also sort of being able to apply a problem to the platform.
Okay. Yeah. I mean, like you said, like expressibility and flexibility, and even then, it's flexibility, easily some of the best things. And I feel like especially for us people with academic backgrounds, like it can be difficult to see why that's really necessary, because we're so concerned with like the validity of like is the research following and flowing, but sometimes the software and the tools that people create and use just completely lack that ability to, quite frankly, use them properly. And it's just like, especially for me as someone who used to work in like bioinformatics, we would run into these problems and stuff all the time. Like for example, studying the human genome, being able to find protein detection sites, and you'd use this process called ChIP-seq. That's the name of the protocol. And there would be like 10 different tools you'd use. All the papers would be published using all these tools and software. We would have no idea how to compare, replicate, or reproduce results and optimize across for greater empirical validity and accuracy. So, from a scientific academic, like pushing forward like findings, and like from that point of view, that's all there as well. But I'm also definitely open to hearing ideas from like just being able to use it well. Like ultimately, Unreal has a much better physics engine than Blender, but Blender is so easy to use. Now I don't know, maybe I'm saying that because I've used Blender for quite a bit. Blender is really easy to use. I appreciate Bradley putting me in touch with. I can just put post in the chat. These are the ones that I'm looking into.
Okay.
So thanks to the recommendations, what I've been hearing.
Yeah,
These are the ones I've been looking into. Elmer, Moose, OpenFoam, and 3D Slicer. Best for these. So once again, just to back up a bit, this is all part of the project on steerable polycapillary X-ray technology for breast cancer computed tomography detection. All right. So all of this really comes from that, and being able to figure out what's the best engine to use for the physics simulations to prove that the chemical physics of what we're discovering and what we're studying is valid, it's relevant, and it's reliable. So yeah. Unfortunately, ComSol requires an academic license, and I'm not a student right now, so I can't actually get that. So.
Yeah.
But thanks, guys.
Yeah. No
I'll
problem.
give you guys a question.
Yeah. And so, actually, the other thing I was going to mention, that one of the problems with a lot of software is like, you'll build a pipeline of different pieces of software for a project, and you can build a really nice specialized for a certain type of problem, and then you'll have to take what you're doing out and put it into another piece of software, maybe to render it. So it'd be like I'd simulate it here, I'd render it here, I might do something else with another step here, and I have to piece those together. So, another thing you'd look for in a platform is either to be able to do those things in the same platform, which is kind of the sort of the idea of multiphysics software, or to like make it easy, to have like a very simple interface where you can export things.
Because I definitely think getting this technology off the ground for the polycapillary approach of X-ray simulation, I might just make my own software to demonstrate it.
Yeah.
It might even be in my interest to do that. But speaking of which, you can do like, I think I mentioned this before. Like you can, so Blender offers functionality with like using lights, using textures, creating solids and materials, and you can actually physically. Hopefully, the groups making those softwares don't go out of business. Yeah. We really need to vouch why the hell this stuff is important to the scientific community. Like we need software engineers. Why the Human Genome Project did not reach its goals by far. Really did not. A lot of it was held back. But excuse me. What was I gonna say? Yeah, like in Blender, you can actually do the double slit experiment, and it doesn't show you the actual results it should, and just in a funny manner. Like not that it really would, because you're not gonna just break the fundamental laws of physics in a software engine. But anyways, so these are all great things to think about, great things to talk about. So that's what I wanted to conclude. So.
Yeah, I think Jesse's point here was good. And hopefully the groups making these softwares or platforms don't go out of business in the meantime. So, a lot of this happens with legacy software, especially in science, where people homebrew a lot of their own stuff and it's not supported for maybe 5 or 10 years down the road.
Yep.
And so you have it, you publish a paper, someone reads the paper 10 years from now, they can't reproduce it because the software doesn't work.
Yep.
Or so that's another problem, and that just comes from some of that is just basically being being a small scale concern where only maybe 1,000 people in the world care about what you're trying to do with the software. But some of it also has to do with not making it open so that people can create forks and improve it or maintain it. If that happens, and that doesn't always ensure that happens, opening it up.
Okay.
Yeah,
appreciate it. Okay, so it's great. It is what it is. And even taking advantage of other dimensions, there's ways of simulating, such as AR, augmented and virtual reality too. Okay.
Yeah.
So it is what it is. So I mean because goodness, I feel like as soon as the results have been shown to be valid using a particular software, a particular tool, time and time again, by the time more research can be published and more findings and stuff are made relevant, whatever tools or engine would show the previous results, there's this question about how reproducible things can be at times. So it's always great to just keep those things in mind and see what's the best you can use and the best you can say. So
yeah.
Okay. Yeah. Anyways, so that's what I want to share. Yeah.
Okay. Well, yeah. Thank you. Yeah. Okay. So why don't we continue with updates? So Shubham or Pakhi, did you have anything to share? I guess Pakhi already gave an update.
I don't have a major update. Share my screen, and I've been working on the behaviors and playing around with some PettingZoo environments. Back when I was working on my proposal, I started with this. And over here, I've been trying to define the contributor agent and maintainer agents, and I'll be adding more an issue class and funding class and all that stuff. And I have a model.py over here. In this, the steps of each agent will be defined, what they do at every step. And over here, I was playing around with some PettingZoo environments. I tried working with Cardpool, but I have not been very successful yet with this. So this is my update for this week, and I can work on the agent-based model using Mesa for this next week, and then I can shift to RL with PettingZoo.
All right. That's great. It looks like you're trying to. You should talk to Himanshu about PettingZoo. I know we talked a little bit about that last year. I think even the year before. That's a good tool to use, but it's kind of tricky to know how to use it. All right.
I have to actually create a custom environment and define all the agent behavior and actions.
Yeah.
So I'll be shifting to that maybe in a week or two.
Yeah.
Thanks so much.
You're welcome. Yeah, and I look forward to getting into the reinforcement learning stuff. It's always fun.
Sure.
So, all right. And then Pakhi is, let's see, She had posted something in the chat here. I have been working on mapper implementation for topological data analysis. And so this is something that she talked about in one of the DevaWare meetings in more detail. And I think that Himanshu, again, has been working on, or he worked on mapper last year a little bit too. I mean, this is something that, people will, it's a common solution to topological data analysis problems. And, just keep working on it, and she'll be updating. And of course, on Mondays, we also talk about this as well. So, you'll have the opportunity to maybe discuss it a little bit more on Monday if you would like. So great. Thank you for the updates. I know people are working on projects, and, again, this is, you don't need to make a huge amount of progress every week. You don't need to wow people every week. You just need to, kind of give a concise update on what you're doing. And but crucially, if you have problems, please, this is the place to talk about them, or even ideas about, how you want to implement something, or how things maybe what people find useful, because that can be helpful. So I'm going to share my screen now. I think Jesse actually, let's see. I don't know if Jesse had, okay. So Jesse had some things in the chat. So the thing he mentioned before about software longevity, he said this is related to some of the pushes for data management as well. So yes, there are a lot of strategies for data management in organizations, and longevity, especially like if you have data and you save it in a certain format and you archive it, and then 10 years down the line that format changes, or the software that interprets or translates that format change, you can have problems. And this has been something with old file formats, not just for data but for software. So like to have a file format open up, you need to have the right software to interpret that file format. And so we have our standard file formats like CSV or JSON or XML, and people have spent a lot of time developing those kinds of standards, which are kind of in time they have been maintained. You have software that can deal with those formats, and everything is fine. But if you take some proprietary format or some obscure format that doesn't have something that can translate it, then you have trouble, and you have a bunch of things that aren't openable. There have been issues in the past with physical media as well. For example, people used to use floppy disks for everything, and they also use CD-ROMs. And those things are, sitting in libraries, sitting in organizations. Can we open the files on them, both from the perspective of the file formats? Can we read the file formats, but also can we access the physical media? So this is a big issue in organizations. Okay, so that's Jesse's comments there.
This is maybe not. This is more something to think about later, or like come back to later. My first point was related to other groups that I'm doing some things with, because in the world of making software products, and particularly when you're trying to deal with scaling or changing, either like kind of Bradley mentioned, you might test in a certain environment, do a very small simulation, then scale up to different levels, or something else. It's very interesting to kind of be both, because I'm not working on, like, there's a software development team and a machine learning team. I'm not on it at my major job, but I do a lot of interfacing with them and kind of connecting them to resources that they needed to do to make the products and the things that we're doing. And it's very in like the wild west of the real world at times, especially when you're trying to do novel things. there's a lot of there can be, but like there's a lot of like there can be a lot of inconsistency, or like especially like a company that's providing a software service or offering a platform can change or can be bought out or can be acquired by another group that's in a different country with a different standard and time zone and like working operations. And it's just there's a lot of like both kind of risk and luck and strategy to dealing with that. And I know that's not anything we're really focusing on talking about here, but I'm kind of mentioning it as a sense of when you're thinking about, right now this is open source code, and if you don't document things well and keep track of things well, the consequences are quite small. But as you go further, keep these kind of contexts in mind, because eventually it will be more and more and more. It's sort of how do you, in a very orthogonal tangent of referencing other projects in our group, like how do you maintain a certain like relative homeostasis of your functionality in this idea, and then the code and the program, and keeping them updated with the constant developments of especially if you're interfacing with hardware or other things that you're trying to do. It's the as you spend more time in these spaces, you realize, okay, it's both maintaining it for yourself, a little bit of demo or deploy in terms of presenting to other people, but also having the means of communicating what you're going to need to do. And especially in industry, which I know is not necessarily open source focus here, but in industry, being able to communicate timelines, like the amount of usage you're going to be using and how that affects costs, and just like trying to get a sense, learning how to feel out what different organizations' kind of functional stabilities are, because that can change a lot. And maybe you'll be in situations where you're just working with very, very stable or established groups that have very specific practices, and there won't be a lot of changes. But depending where you are on kind of like the startup spectrum versus like using really innovative like technologies and like the things that support them functioning, they all require different amounts of this kind of awareness. So just thinking like, okay, when I'm thinking about documentation, when I'm thinking about what my project is, when I'm thinking about how to extend this shift from I don't know, a project that's sort of abstract from anything else in the world, to a project I do want to be connected to the world and people, and to maybe having a flow of economy through it too, or like it being marketable, or it being even sustainable open source, like starting to develop this context and intuitions and experience, and getting to realize like, okay, like how do I keep this idea connected to other things? I think that's sort of my. It's a bit of a big theoretical, hand waving thing I'm saying here, but also, like if you ever want to talk about this stuff, like there's a lot of good experience here. Like there's things I'm kind of dancing around saying a lot of things that happened recently in other places I'm working with. That's why I'm talking this way. But it's like it's a challenging thing, and you realize like a lot of groups don't necessarily have their stuff together consistently. And when you're venturing into that space, the more you can kind of have your stuff together, or learn how to have communications about understanding and like getting the feedback about that is going to be key. So that's my sort of I don't know, slight soapbox of the day, I guess. But I'll leave it at that.
Yeah, that's great. I think that this idea of awareness of things in projects, like what are the things that you need to have that are specific to your type of the technologies you're working with, the kinds of problems you're trying to solve, because it's not a one size fits all solution, right? You have to have different types of. You have to be aware of different types of things for different types of approaches. That's true. So what I'm going to talk about next we're going to get a little bit into this paper that I sent Hussain about different types of software for multiphysics. We'll talk a little bit about, how from an open source perspective, and then we'll talk about lab management. So Hussain asked me a question about COMSOL, and COMSOL is a multiphysics engine, meaning that you can take the software, you can simulate things at different scales of like different size scales, different time scales, and depending on your system, you'll have different types of physics operating. So, you might have a very small physical scale, spatial scale, and you might have to simulate laminar flows. You might have larger time scales and size scales. You might want to simulate turbulent flows. There are different physics at different scales. As you approach the nanoscale, you might want to simulate quantum effects. I don't know how COMSOL handles that, but the point is that, in a lot of engineering problems and a lot of biophysics problems even, you have these different types of materials, different types of scales that you're dealing with, and you have different types of physics that you want to simulate. Sometimes they're all consistent. Sometimes, you have to treat things differently. You have to coarse grain them or pick the size of your unit of analysis differently and so forth. So that's what the problem is. And so COMSOL is one of these platforms where you can do all of this in one platform. Now, it's questionable whether you can do it very well in all for all phases of a project. A good example of that is in DevaWorm we have Susan, who's working on this problem of tensegrity or biotensegrity, which is where she wants to build these ultra stable structures, but she wants to do it in biological tissues. And so COMSOL can handle tensegrity in like mechanical systems, and it works just fine there. But the problem is that that's not what you have in biology. You have different types of materials, and when she tries to simulate those, it doesn't work very well. So, there are a lot of things where we'd like to extend COMSOL to deal with biophysics problems like that, but we can't because COMSOL is closed. It's proprietary. You can't really add on with your own code and so forth. So I found this paper for, plus, we have the license issue, which means that if you're not a student or if you don't have access to a certain type of license, it costs a lot of money to access. And this is a problem not just in like scientific software, but organizational software, especially like smaller organizations where you have to buy a bunch of licenses for software, and it gets pretty expensive to have, more than one seat. So like with VR or with 3D modeling software, you have to buy the licenses per seat. So Maya is very expensive, which is the sort of the gold standard for a lot of movie animations. Those seats are extremely expensive. So, you can only have like one copy, one person doing the work. Of course, if you have a team, that's hard to maintain. So you might want to use something like Blender or something like Unity. And of course, you have to pay for Unity, Blender. The point is that you have to pick your tool based on what you can afford, based on what you can support for the long term, because your project might go on for a while, but also for these other functionality aspects. So I sent Hussain in this paper a survey of open source multiphysics frameworks in engineering. This is a Procedia computer science paper, and this kind of goes through the alternatives to COMSOL, which is a multiphysics engine. But they have these multiphysics frameworks because it's a larger set of problems that people have worked on. And the reason why we have software in the first place for this is because people worked on different systems in physics, in chemistry, and other areas in biophysics, and they have these problems. They have these massive sets of equations, which you could take like something like MATLAB or Python, and you could simulate each equation, and you could solve differential equations, but it would be extremely expensive computationally, and it would take you forever, and you still wouldn't have everything integrated into a workflow. So people use multiphysics frameworks to do this all in one place. Console is an option, but it's expensive and it's not open. So we have these open source multiphysics frameworks. And so this talks about this is a systematic survey of these frameworks in engineering domains. So a lot of engineers want to have that package where they can like not have to deal with all these, integrating all these equations, simulating differential equations, dealing with the moving parts, and so forth. They just can't afford to do that in their workflow. So, you have in engineering domains, from mechanical engineering to chemical engineering and so forth, you have different problems that you're dealing with, but you want platforms that can just kind of plug and play with those research problems. A thorough search for the available frameworks with both academic and industrial origins have revealed numerous candidates. People have gone through, and it's kind of hard when you're looking for a sort of a software replacement for some proprietary software. There are all these pieces of software you'll encounter. You might do a Google search for open source alternative to console, and you'll find a bunch of options. And some of them are maybe like well maintained, some of them are not. Some of them are very limited in functionality. Some of them are not very well, they don't run very well. So these are all things you have to watch out for. And so what they did in this paper is they considered a couple of key characteristics. One was project size, meaning that you have an open source project that backs the software. How big is the project? If it's small, we can assume that maybe it isn't very, complete, or it isn't well maintained. But that's, an assumption. Maturity, meaning that are the features mature? If I go in, can I use the features out of the box? Or do I need to have some development time or some people who can develop the feature out for me? So if it's like some sort of analysis tool, it could be like, things that fit into the physics engine. We might have to spend significant time developing our own tools for it, which is not great because you want to take things right out of the box, but a lot of times you can't because the functionality isn't there. And even though it's open source, that costs you time and effort. And visibility, meaning that, do people know about the platform? Do they have a community that is active, a community of users, a community of contributors, whatever? So, there are a lot of options. In science, people tend to homebrew stuff, which is maybe not great from the perspective of like having a mature tool, because if I homebrew something, it might be for a PhD project. People kind of, leave the lab and then it doesn't get maintained and it falls into disrepair. So it's always good to find something with a really good sort of track record. They selected Elmer, OpenFoam, and Salome for detailed analysis. So they picked these three options for further analysis. All the public documentation for these tools have been manually collected and inspected. Based on the analysis, we built a feature model for multiphysics and engineering, which captures the commonalities and variability in the domain. Hussain asked Morgan a question about 3D slicer.
I was asking that, yeah. No, Morgan had originally asked. Morgan mentioned earlier that 3D slicer is meant for would be a good one to look into. It looks like it's for imaging, right? Medical imaging.
Yeah.
Okay. So that's not relevant to what I'm doing though.
Yes, no, it actually is. It started as an interventional radiology. I can say more about it later.
Oh, well.
In finishing this up, it's just that they've in turn validated the resulting model, which is this model for evaluating these tools via two other tools: Kratos by manual inspection and OOFEM by means of expert validation by domain experts. So yeah, this is where they do this sort of study of the open source domain. They come up with these candidates. They build this feature model. This is a feature model of a car. If I can zoom in here to show what this looks like. This is where you have a car and you have this hierarchical tree. So every car has a body, a transmission. It might be able to pull a trailer, and it has an engine. So, if you're thinking of building your own car, you want to have these features included in the car. Or if you're thinking of building your own software platform, you have to have these features, or people expect these features in the platform. Then, like a transmission, you have options. You can have a manual transmission or automatic transmission, and an engine can be gasoline or electric. So, you have these mandatory features, you have these optional features like pulling a trailer, you have these alternatives to the mandatory features. And that's how you think about when you design your feature space for your software, how that should look. You don't want to have a multiphysics software that doesn't have the features you need. And so, to the point of what we were talking about just before I started this part, you could have a software specialized sort of for radiology, and you can adapt it to different purposes as long as you have the correct features in place. That's not too much of a problem. So that's what a feature space looks like. This is, they did this iterative modeling. So they gave a small example of this. So they did this iterative modeling. So this is Elmer at the top. Elmer has preprocessor and parallelism. The preprocessor is mesh generation and partitioning. Parallelism means that you have to have technology for parallelism, which could be MPI or OpenMP. And then infrastructure for parallelism, which would be either the grid or a supercomputer. So what you have is this platform and has these features. And then it has to sort of do things like in terms of interacting with the computational world. So you have this preprocessor, which does mesh and generation and partitioning. So it's building meshes. And then it's operating on a certain technology. The technological standards can change over time, or you might have people who prefer one over the other, and you want to have interoperability. The grid, depending on where you run the program, you want to be able to support either a grid or a supercomputer. So you have to think about these things downstream as well. You don't want to have think, well, okay, we have this software with these features. That's great. How do we run it on the hardware that's available? Well, we either can't run it on, we can only maybe run it on a very specialized graphics card, or it really is going to have problems with performing on most hardware. So, again, Elmer plus OpenFOAM, we get this preprocessor step where we get mesh generation, manipulation, and validation. So adding OpenFOAM gives you this mesh validation, which is important for people who do work on benchmarking and things like that. The parallelism aspect, we now add CUDA as one of the technologies, and we add GPUs as infrastructure. So again, we can expand our universe of how we can run the software. And so that's kind of some of the things we can learn from this paper in terms of developing open source software and how those, how we can think about that. And then thank you, Pakhi, for attending. And Hussain said the real question is what funny name you want to give your software. Yeah, it always.
I mean, speaking of which, yeah, these are all great points, and that's why I really appreciate Bradley sharing that paper as well too. So thank you so much for going over that. And yeah, it's important. And I did mention these potential areas of work, like even me potentially making my own software, making my own engine.
Yeah.
For these simulations themselves, depending on what I may specifically look for or need. Like the ones that I mentioned, for example, because once again, this is chemical physics, so X-ray simulation approaches, which Elmer, Moose, and OpenFOAM would be good for. Ultimately, though, like in terms of like when it comes to the point where you should make your own software engine, when you should make something differently, or when things like really like if nothing is just like working out for your specific needs, and it's just those things are not working, then it's like if you think you can make it yourself, then like by all means, there's people can definitely go ahead and do things like that too. So once again, yeah, like there's this one of my friends who's interested in game development. He's a video game developer. He mentioned to me a game that was released recently called Animal Well, and it's been pretty popular. And the guy who made it, he made the game engine himself. Like he made the game engine himself. A lot of games use already built engines like Unity, Godot, Unreal. He made the engine himself for that game, so that's pretty cool.
Yeah. All right, so that's good. So the other things I wanted to talk about was that I wanted to congratulate Jesse and Jen for creating the start guide for et.al. So this is for the summer cohort. This is for both the Google Summer of Code Scholars and the Open Source Development Scholars. So this is just our onboarding guide for et.al. This is on Notion. So this is the Notion page. We have communications, meetings, GitHub, so deliverables and outputs, additional opportunities to contribute. So I think those are great. This is a great piece of work here. For meetings, we might add in the DevoWare meeting as well. But it's, this is good. This is good. This is a very good overview of everything. Thank you for your efforts on that.
Bradley, did Mel get in contact with you about stuff?
Yeah, he contacted me in the Devo or in the OpenWorm Slack. So
I just happened to see a message there that was like, hey, just explain some stuff.
Yeah.
So that's cool. Yeah, okay. Yeah, the start guide is a very small thing, but there's more stuff in the works than here today.
Yeah.
I'm kind of partially here, so I won't say a whole lot more.
Well, that was very good work. And then final thing I wanted to talk about was this. This is an article that was in the Slack in the in the open source GSoC channel. So this is from the Wojtek lab. Bradley Wojtek is at UC San Diego. He does a lot of stuff with neuroscience, of course, with organoids, and then I guess he's connected to the organoid community through Alison Moultrie. And then he does a lot of data science stuff as well. So this is a blog post on lab management. And so this kind of goes through some things about, so, in labs, and we've been talking about software development, and, scientific labs aren't really in the business of software development. They're usually in the business of doing research, maybe some education. We're actually kind of unusual for a lab in this way because we do more education and like some open source software development discussions and work. It's not typical of a academic lab, although that's kind of changing. And sometimes, you're forced in by necessity to do software development, which is maybe not great because then you're not really adhering to the standards of software development. So you do these things that you're not really suited for. But in any case, this talks about lab management, though, is particular, and in terms of like how you kind of develop workflows, how you sort of solve problems and manage all of the sort of the technology, and how do you make yourself more productive. So this was several months ago. There was an email thread going around among some neuroscience professors asking for advice on lab management software to help us get more organized and productive. So this is where you might do like things like ordering different equipment. You might make decisions on how people are doing what tasks. You might have things like in psychology, you have subject pools where you have to manage those sorts of things. But there's a lot of money that's been spent on lab management techniques and software. And so this is something that, people have to navigate that space as well. So this is, it's very helpful to always know how to do this better. And in his case, they use GitHub a lot. And a lot of times, if you're in an academic lab, GitHub isn't the go-to to manage things like files or projects or anything like that. So that's something that, depending on your lab, if you're computational, you probably know GitHub. But if you're not computational, you might not use GitHub. And so this is one way to do this, is to use GitHub, use sort of the share file sharing and version control aspects of GitHub to manage things. and some of the workflow tools that we talked about last week, like Kanban boards and other types of feature planning tools. In my lab, we manage a lot of work at GitHub. It's traditionally this sort of platform for hosting and maintaining computer code and being able to share it, but it can share all sorts of files, like we talked about, though, with assets for VR. Sometimes you have limitations on what you can use. This means that you can use it for a lot more than just software development. Over the years, we've become more reliant not only in its file hosting and tracking capabilities, but also its built-in project management features. So yeah, like, GitLab might be better for some types of file sharing, but GitHub, they have different types of project management features. We have Kanban boards, feature trackers, other types of things. And there are other tools you can plug in, like ZenHub and other types of tools and approaches to managing your projects. So this is a very good, this kind of relates to sort of going from research and development to project management and how those things intersect. So they have a main org, Wojtek Research, and within that org there are many repositories. So this is on GitHub, where you have the Wojtek Research GitHub, and then within that you have many repositories, one for each project. And so, the way they break it down in GitHub, of course, is that you have each, this is a repository here, which is Wojtek Lab, and then you have your directories and files and your project management tools and your issues and pull requests and things like that. So you can imagine that if you're in a project, this could be very useful, especially if you're not used to using it. Now, other projects, it might not be as useful. Just depends on what you're doing. So they actually, in the Wojtek Lab, they run their own open source Python packages, these three here. And, this allows them not only to share within their lab, but to publish things for the larger community and update things and provide releases and things like that. Then they have, of course, the helper repos, like the main repo for, onboarding, or resources repo for lab processes, the tutorials repo for interactive notebooks and other types of demos. So, there are different ways you can organize this. We organize things not only in GitHub, but also on Notion and other tools. We've gone through this PettingZoo in the past, so we've kind of worked out what works for us. And, that always changes with the technology. So I know Jesse's a big fan of sampling the different technologies, but also, he likes Notion, and, it's just personal preference. It's what works well for the org. And then also, what is sort of the standard in your field, if there is one. What kinds of things are you doing? Like, are you working with a lot of, imaging files? You might not want to put those on GitHub. You might have a different method for that, but there might be things like Python tools that you might put on GitHub and manage that way. So, go ahead.
One thing, because kind of blending what I said before and this, like, if you can help either if you're doing something yourself, then it's all on you, obviously. But even if you're joining a company or a lab or another group doing stuff, thinking about how it's this interesting line between trying to do things exactly as are given to you versus suggesting things to be done differently, or even something like I've been in situations where, and this is kind of the case even in this lab as a lab manager, but I'm talking mostly about another group specifically, where I had to, like, in some cases you're going to be in the only structure that's going to really exist long term is the structure you make and you ideally collaboratively make with other people, but sometimes it's just going to be you. But even like you making that structure yourself is important. What's cool about GitHub in this sense is that it's really stable, and it's been interesting to kind of see. Before I came to the lab, I didn't Bradley uses a bunch of there's a lot of archives and Google documents and Google Drives, as we talked about before, and most of our history is on either the GitHub orgs or the legacy GitHub ORL orthogonal lab repo page. So a lot of things are there, and I think for files and a lot of conceptual things, it's a great way to go. I haven't fully looked at all of the Vortex resources,
Yeah.
but I'm glad we're going through this to kind of get a sense of what another lab that I think their primary like project management situation is this specifically. And I know that they do like I think you're about to get, I don't know if you just talked about it or about to get the Google Docs template paragraph, but like having those like starter things to decrease the sort of the startup friction or the activation cost of all of that stuff is good. And we have done a few versions of those here in our lab, like some how-to guides, but yeah, we can go on with that.
Yeah. Yeah, a word about that. What they do here in this lab is they have these paper templates. So you would have like something hosted on Google Docs. It would give people a template for working out the structure of a paper. So when you task someone with writing something up, you could do this. You give them a template, they fill it in. We can do this with documentation as well, and oftentimes that's more useful than just telling people to write it up, and they write it up in their own way. You can also generate documentation from like R code actually now. So this is another tool that we can use. We can integrate with GitHub. We basically do our work. We generate some documentation. We can then modify it, and we're all set. And even we can do things like build these executable papers. So we want to take what we're doing and we want to fit it into maybe like a larger workflow, like a paper. So eLife actually allows you to create executable code versions of a paper. eLife has like these tools that they've worked on as part of their open source open publishing groups that they've hosted. So this is where you have code and you have a paper, and you want to be able to take that code and run it, and then basically reproduce the paper ideally. So this is one of the things that they're working towards, and this is the kind of thing that this sort of standardization affords you. So it's very good, and this of course shows some of their issues that they're building. So they're using issues and they're tracking issues. So a typical lab meeting, you might ask what people are working on and having these issues. And this doesn't seem like a very big deal to open source people, but like for an academic lab, this is actually quite a big deal. So you have to think about what culture you're coming from, and then what the expectations are, and how, if you adopt open source tools, it can benefit you. But also, projects who doing other things like, working in other domains, non-software domains, this can be helpful as well. So I think that's enough for that article. That's in the Slack. So look at that, at sort of the details of what they're doing to get a sense of sort of some of the tools that you can apply to project management in groups like that and organizations if you're interested. So that's all for today. Did anyone had any other things they needed to say before we go?
I would just offer, I would just offer, like, for people who going through the summer cohort, and you're not really sure, like, you have questions about even just organizing your stuff, or how where to put it, or even like basic things like that. Like, I would just reiterate that you're not expected to know all of this stuff. We're talking about these things, and we have some very experienced people in the lab. We have some very experienced people here, and we have people who are doing a lot of this stuff for the first time. So we're kind of talking about things that are maybe mid to high level concepts at times for like project management or other things too, and just realize, especially people who are, I know some people haven't been able to make the meeting and are watching the meetings like after the fact, but you can reach out and say, hey, you talked about this, and I don't know how to apply this to my project. I mean, like, that's we encourage that, and we expect that. So just just a reminder that we're kind of saying all these things and referencing stuff, but if you want to, get specific feedback of where you are in documentation or your version of project manager for the course, or putting things on GitHub, or using different storage approaches or whatever, like you can just reach out about that, because that's good and okay to do.
Yeah.
That's my closing point.
All right.
But it's a great meeting, so thanks everyone.
Thank you. All right. Talk to you later.